So welcome to the AGN notebook. So some of the things Pancho presented in the supernovae tutorial will be also mentioned here, but focus mostly on AGNs, not supernovae, of course. So, well, first of all, you need to install the client to run this notebook. This is the command to do it in Colab. You can also do it in your own computers. If you go to this link, you will see the instructions. And then we import the package doing this, and we define a client doing this. Okay, so these are the basic requirements to run this notebook, some basic Python packages to plot, pandas to manipulate the data, AstroPy, and also AstroQuery to do the net searches. Okay, once you have that ready, oh, sorry, there is also some external packages. So these are almost the same requirements that Pancho presented in the supernovae notebook. The only difference is we are also using Seaborn here, which is a package to plot very nice figures. Okay, so this is an introduction you have seen a lot during these tutorials, but it's important to mention some particular things for the case of AGNs. So we have this stamp classifier where one of the classes is AGNs, and in particular, this classifier identifies galaxies with variations in the nucleus. So that's the AGN class for the stamps. And for the case of the Likert classifier, we have 3 classes of active galaxies: quasars, AGNs, and blazars. We also have some other stochastic classes like CV nova and Young-Ser objects. And also one of the main contaminants in the selection of AGNs in general is the class long period variable, because some long period variables have irregular Likerts, and they can be confused with AGNs and also the semi-regulars. So these 3 are the main contaminants. Also, sometimes you can confuse them with supernovae, but in this classifier, that's not the case because we can clearly say when a source is transient. Okay, so this is the taxonomy tree that you also have seen a lot during these tutorials. Here are the blazars, quasars, and AGN classes, which are part of the stochastic class. And here are the long period variables, which are in the periodic class, but as I said, when you classify AGNs versus all the rest without a hierarchical taxonomy, it's very easy to confuse AGNs with long period variables. And this is the definition of the 3 classes of active galaxies. We have the AGN type, which is similar to a cipher 1, which means a source that is dominated by the host galaxy. And we obtain the labels for this class from the Milliquas catalog, which is a very large catalog that compiles all the known AGNs in the literature. And the case, in particular, the classifier, the class A, is the one associated to host dominated sources. We also obtain some additional targets from this catalog that use SDSS spectra to classify sources that are dominated by the host. And then we have the quasars, which are the nucleus dominated sources. All of them comes from Milliquas, and you can select them using this Q class. And then we have blazars, ALeRCE objects, and flat spectrum radio quasars, and we select them from the Roma catalog and the Milliquas catalog. But all these classes are, it's not you cannot do clean cuts to separate them, so you can have some confusion between the classes, particularly for the AGN and quasars. It's hard to say for sources with intermediate luminosities. It's hard to say when the source is AGN or quasar, so you still have some confusion. But at the end, the motivation of doing this separation is just to be able to select different populations of AGNs or quasars. Because if we put these two classes together, you will bias your selection towards the most dominant class, which is the quasars, because there are several known quasars, but the number of known host-dominated sources is lower. So if you want to be able to find different populations, it's better to do this separation. But at the end, what is important is the fact that these sources are classified as active galaxies more than is an AGN or a quasar or a blazar. You can, of course, consider these classes, but the most important thing is to say, okay, this is an active galaxy. The separation is mostly to be able to detect them easily from the data because they have different observational properties. So this is the confusion matrix. Here are these three classes. As you can see, there is a lot of confusion between them, but it's much better compared to supernovae. And the confusion we have found that is mostly because of this difficulty in making strict cuts for sources with luminosities of around 10 to the 45 ergs per second. It's hard to say when it's a quasar or an AGN. So we have these results here, this confusion. But if you see the classification of AGNs, quasars, or blazars as a single class, you can see here in these recall curves that we are obtaining very good results using this classifier. So the recall curve tells you how many times you recover a source that is a known active galaxy as an active galaxy. And when we have both bands available, the classification is almost perfect. And in some cases you have one band, so it's important to see what happened in those cases, but also we can do a very good selection when we have only one band. Okay, so that was the introduction. So in this notebook, you will find examples of how to plot light curves, how to query the database using the client, and how to query the database using a direct connection. So something different compared to the supernovae notebook that Pancho presented is the fact that during this notebook, we will use mostly the corrected magnitudes, not the difference magnitude. So here is the formula that we use to convert these difference magnitudes to the magnitude that you will measure if you have photometry from the science images. So what we receive from the ALeRCE is not the science image photometry, but is the difference image photometry and the photometry of the reference. And we also have information about the sign between the subtraction that you do between the science and the template. So when the template is brighter than the science image, you have a given sign, and if it's the opposite, you have another sign. So this sign is provided in the ALeRCE, so you can have an idea of what was brighter, the science image or the template. If the template is brighter, the sign is negative. If the science image is brighter, the sign is positive. So it's very important to correct this properly in order to obtain the real shape of the light curve, not fake shapes. And I will show you examples in a couple of minutes. So we will start plotting one light curve, and I will take this source as an example. This particular source was classified as a changing look liner in this paper. This is a recent work done by the CTF collaboration. And here, these are light curves that are similar to, are functions similar to the ones that Francisco presented in the other tutorial. but I did some modifications to work with the correct magnitudes. So this is to plot the difference Lie curve. If you want to plot the difference Lie curve, you need to use these, the MAC-PSF and the sigma-PSF. If you use these columns, you will obtain the difference magnitudes. So this is similar to what Francisco presented. And then if you want to plot the corrected Lie curves, you need to use MAC-PSF core that use the formula that I presented before. And this is the error. So sigma PSF core X, and why X is because we are working with extended sources. So doing this, you obtain the corrected Lie curve, not the difference Lie curve. And we call it apparent magnitude Lie curve. And this is a function to obtain the data and to plot the Lie curves. So here you give an ID, you ask if you want to plot the Lie curve, and if you want to plot the difference Lie curve. So if this is true, the function plots the corrected Lie curve. And here is the source that I mentioned, the changing look linear. So this is a source that was classified as linear. So you won't expect to see variations in the optical range. And now it has a lot of variability, and they classify it as a changing look linear. So this is the difference Lie curve. You see the G band in red and the R band in, sorry, the G band in green and the R band in red. And in triangles to see the upper limits from the non-detections. And in this case, the Lie curves in G and R are very similar. The source is very blue in the difference image. But if you plot the corrected Lie curve, now the source is very red. So the R band is much brighter now. And in this case, it's not easy to see the differences in the shapes of the Lie curve because the sign is always positive. But here I present another example where these changes are more extreme. So this is this galaxy Markarian 817, and it's very variable. This is the difference magnitude Lie curve, and this is the apparent magnitude Lie curve. And you can see here how this behavior at the end of the Lie curve was missing here. It's very hard to see this in the original difference Lie curve because in the difference photometry, they always report positive values. So it's hard to say when there was a change in the sign between the difference of the template and the science image. So you need to always use the corrected Lie curves in order to find the real shapes. So in this case, we have this activity, increase of activity here that maybe is produced by a microlensing or a flare. Who knows? We need to investigate that in more detail. Okay, so if you want to use the CTF data for AGN science, you need to use the corrected Lie curves, the apparent magnitude, not the difference magnitude. Okay, so and for the rest of the notebook, we will use the corrected Lie curves. Okay, and so as in the other tutorial, we will plot also the Lie curves corrected by redshift and by extinction. So here again is a similar function, the one that plots the corrected Lie curves, but we include these extinction and redshift parameters. So if there is redshift available, we will correct the Lie curve by redshift, and we will also compute the absolute magnitude of the Lie curve. So we'll skip this. This is the new Lie curve to obtain the data, sorry, the new function to obtain the data, and to perform the query with net using Astro Query to obtain the redshift and the extinction. And so here you do it. And then we also plot the stamps because it's always nice to see the stamps. And here are some examples of using. So here we have this. We start with the same target as before. So this is the result that we obtain when we do the net query. And this is the redshift of the source. So this is the apparent light curve, and in these lighter squares you have and circles you have the light curve corrected by extinction, and this is the light curve corrected by redshift in the x-axis and in the y-axis. So you have absolute magnitude here, and this is the time in rest frame. And these are the stamps. So you can see here a very nice example of when you see in the template and in the science image the central part and the host galaxy, but then when you subtract the images, you just obtain the variable central part. And this is another example for a source where we don't have redshift available, but we can give the redshift by hand using this function. So in this case, the redshift wasn't available from net, but we can obtain the redshift from this SDSS catalog. And this is the light curve and the stamp. Okay, so this is just a small example of how to use Aladdin. This is a way to how to use Aladdin in Colab. But if you want to see examples of how to use Aladdin in a regular notebook, you can go to the use cases GitHub repo of the ALeRCE broker, which is public. And if you go to the Active Galaxies new database notebook, you will see an example of how to use this in a regular Jupyter notebook, not in Colab. Because in Colab, we had to do some modifications in order to use Aladdin here, because otherwise it doesn't work. And this is the Aladdin image that you obtain for the same galaxy we have been showing during this tutorial. Okay, but that's not very useful if you want to work with several sources. So now we will see how to query multiple candidates using the client, and then how to do that by using the database. The direct connection to the...
10 minutes, there are 10 minutes left.
Are you sure? Okay.
We can explore it.
Okay. Okay, we'll go fast. You already see this. This is the client. If you do this, you will see all the parameters that you can give to the functions in order to make it work. So I will show you some particular examples for the selection of AGNs and quasar candidates. So it's very easy to use this. For instance, you can say, okay, give me all the sources classified with the light curve classifier that are classified as AGNs with this minimum probability, with this number of detections. So you can select here how many detections you want, and order it by probability, and then the total number of candidates, so 3,000. And then this will, and if you select the format pandas, the output will be a pandas data frame. So here you see the output. So you have the ID, different properties like colors, and the classification and probability. And we do the same, but with quasars, and we obtain a list of 3,000 quasar candidates. Okay, so here we have colors, so we can plot histogram of the colors. And first I plot the color of the corrected photometry.
Paula, sorry, I just want to confirm that you were right. There were 25,
yeah.
no? Yes.
Yes.
Sorry.
Okay. When you see the corrected light curves, the colors for the AGNs candidates are much redder than for quasars. And this is because these sources are dominated by the host. So you expect to see redder colors. If we don't separate these sources and we just classify sources as AGNs in general, you probably will miss these sources because the classifier will be biased towards the quasars, which are the dominant class, because in the label set, there are around 20,000 quasars and just 4,000 AGNs. So it's very important to separate them if you want to be able to detect sources that are dominated by the host or by the core. So that's why we separate them in two classes. And this is what happens when you use the difference light curves. The colors are much similar. And this is because in the difference light curves, you just see the variable part, which is blue, because it's the AGN emission, not the galaxy emission. So in general, they will have similar colors. So this change in color is produced by the fact that the AGNs are dominated by the host. So the color that you're measuring is the color of the host. Okay, so using the functions that we used previously, I will plot some random sample of AGNs candidates. So some of them are known and have redshifts, but also there are some others that are unknown. So this is a very nice candidate. This is a candidate with a light curve that is very incomplete to have these huge gaps here, but this is consistent with stochastic variability. And you can see here that this source was classified as galaxy innet, but it's in fact an AGN, very variable. Here are other examples and stamps. So in general, in the stamps, you will always see a central emission. If the emission is not centered with the host, it's probably a supernovae and it's an incorrect classification. So there's other examples. Okay, but this is more interesting and more useful, how to query candidates using a direct connection to the database. So here's where we are going to use the SQL knowledge that we learned from Camilo. So we will use this package, scopg2, which is a very nice package to read Postgres databases. So here we read the keys that we need to connect to the database. All this is public, so you can find the keys in the ALeRCE repo, the public one. And this is how you connect. So you need to give the name of the database, the user, the host, and the password. And you can see all that information here in this JSON. So if you want to know all the tables available, you can do this, and you will see all the tables. So here is the description of these tables. The most important ones for you are the detection table, where you can see the light curves. Here are all the light curves. The non-detections can be also useful, but for AGNs are not that important. And the object table, you have basic information about the objects. In the probability table, you have all the classifications. So this is very important. In the reference, you have all the information about the reference image. And in the features table, you have all the features computed by ALeRCE. And in the cross-match tables, you have all the external catalogs for which we have computed cross matches. Okay, so if you do this, you can see all the columns available in each table. So in the sections, you have the object ID, the date, the filter ID, and the magnitudes, the photometry. So it's important to select properly the filter ID. So for the case of the G band, the filter ID is 1, and for the case of the air band is 2. Okay. So now we will do a query where we will select all the sources classified as AGNs, quasars, or blazars, and we will define a minimum number of detections, because for the case of active galaxies in general, it's not very useful to, it's not very easy to classify the sources when you have less than 10 epochs. You need a given amount of detections in order to be able to perform a correct classification. And also you need a proper length in the light curve, the time, the total time that the light curve covers. So here we filter the light curves by the total length and the total number of detections. So this is an SQL query. If you don't understand SQL, it doesn't matter, you just copy this and you just need to change this, because here we provide the restrictions in the number of detections and in the length. This is the minimum probability we are requesting. So in this case, 0.4, you can change this if you want and request higher probabilities or lower probabilities. And in this case, we are only considering AGNs, quasars, and blazars. And here we are saying, okay, give me the object ID, the classifier name, the class name, the ranking, and the probability. So the ranking is, it tells you, okay, so this source was classified as AGN with a ranking of 1, so that means that's the highest probability. So at the end, the source is classified as an AGN. And when you do that, you obtain this table. So we have 34,000 candidates of AGNs, quasars, or blazars. And we now select only the rows where the ranking is equals to 1. So we only get the maximum probability. And here you can see the total number of quasar candidates, the total number of AGN candidates, and the blazar candidates. So you can see that most of the candidates are quasars. And this is just a simple step where we save the IDs of the objects, because we will use this for the rest of the notebook. So the object IDs are the CTF identifiers, and they are unique for a unique source. Okay, so from this, we obtain the classes and probabilities, but now we can also query features and photometry from other databases like PanSTARRS. So if you want to obtain the photometry from PanSTARRS, you can do this. So this is the query that says, okay, give me the object ID, the PanSTARRS G, R, I, and Z photometry, and the SG score. And the SG score is very important because it's a morphology score that tells you when a source is extended or is a point source. So when SG score is equals to 1, that means the source is point source. And when it's 0, it's an extended source. And here I'm saying, okay, but don't give me the total table. Give me just the object's ID that I selected before. So here I'm specifying, okay, give me just the IDs that are of my interest. And when you do that, you obtain this table. So you have your object IDs and the photometry. And you can now compute colors, so G minus R, R minus I minus Z. And if you do this, you will include this to the object data frame that we already defined in the previous step. So now you have the same table as before, but now at the end you have this, the pan-stars photometry and the XG score. So you can plot now a color diagram. So we will use G and R minus I for AGNs, blazars, and quasars. So this is just a simple plot using a scatter plot from matplotlib, and we also plot with Seaborn the density, because since we have too many points, it's hard to say just using a scatter plot where are located most of the sources. So we use Seaborn to do that. And this is the final plot. So in blue you have quasars, in red AGNs, and in green blazars. So you can see here in this color diagram that quasars are mostly located in this blue part of the diagram. Normal quasars or regular quasars are always here in this area. So when you perform a color selection, you will always find these kind of sources. And then AGNs are located here, where normally you find galaxies and stars. So if you exclude variability features or just use colors to select the sources, you will miss the sources because they will be confused with stars or galaxies because they are in regions of this color diagram where quasars are not normally found. And in the case of blazars, you have also blue sources, but also red sources. So that's why it's very important to use variability information to classify different populations of AGNs. If you just use colors, you will obtain just these regular quasars, but if you want to find these sources that are dominated by the host, you need to use variability in order to obtain more confident classifications. And this is a plot to see the SG score. So as I told you, this varies between 0 and 1, and values closer to 1 imply that is very likely a star or a point source, and values closest to 0 are extended sources. So this is the same for quasars, AGNs, and blazars. So in general, AGNs or host-terminated sources have very extended shapes, and quasars and blazars are point sources. Okay, so now we will carry some variability features that are relevant for AGN science. So we have the ER parameter, which is a new feature that we use in ALeRCE, and it's very useful to classify sources that have stochastic variations. We have the typical dumb random walk features that has been used for a long time in the AGN field, and also the excess variance and the structure function, which are also very popular, but a new one that is a very useful set of features is this Mexican hat power spectrum feature that I will show you later how it's defined. So if you want more details about all these features, you can go to the paper. We have in the appendix and in the main text of the paper a very nice description of all these features. So if you want to query these features for the sample of candidates that we selected before, you can do this. So we are selecting all the features from the Mexican hat power spectrum model. These TP are the dumb random walk models. We call it TP here. It's just to query it because they are the only features whose name starts with TP. These are the structure function features, the excess variance, and the regular model phi parameter. And by doing this, you select only the OEDs of the objects that you already selected in the previous step.
No, it's really 10 minutes.
Okay. So when you do that, you obtain this table. So you have for one feature, one row. The problem with that is it's not very easy to manipulate. So we do this. We use this pivot function in pandas. So we order so now we have one row per OED, and every column will have the features. So now it's easier to manipulate the data. So when you do that, you obtain this table. So now for each object, you have one column with each feature. And then we do a join with the previous table in order to have features and classifications together. Okay, so now we have this final table where we have the classifications, probabilities, the pan stars, colors, and also the features, the variability features. Okay, so now let's explore these features in more detail. So one of the most interesting features that we are using now in ALeRCE is this Mexican hat power spectrum features. This method was proposed by Patricia Arevalo, who I think is here in the room. Thanks, Patty, for your very nice model. So the idea of this method is to isolate variability of a given time scale and then compute the variance of that time scale and use as a feature. And this is very important because for instance, AGNs and long period variables can have similar likelihood if you see variability at long time scales, but if you see variability at short time scales, you will see that long period variables doesn't show variability at all because they just vary at long time scales, but AGNs vary at different time scales, so you will still see a high variance for short time scales. So it's very important to use this new set of features to separate active galaxies from variable stars. So this is a huge function, but the idea is just to plot the features. So it's quite long, but it's just to create this set of plots. So we have, again, quasars, AGNs, and blazars, and these are the Mexican hat features. So you have low means low frequency. So this is long time scales, and high means high frequency. So this is short time scales. And this is the ratio. So with these ratios, you can have an idea of the slope of the power spectrum.
Paula?
Yes?
We have one question from Priyanjali. What other improvements are possible for classifying AGNs?
Okay, so maybe you can do a better job if you include also karma modeling, but the problem is very expensive, and with the length of these light curves, it's not very easy to obtain nice features. But once you have a lot of data, several years of data, you can compute karma models, and probably those are better to properly model the aging light curves, but it's very expensive. So
there's also multi-wavelength or different surveys, so you could fold in Gaia and WISE and do SED fitting.
Yes.
You could probably do more with that.
Yes, so from the side of variability, you can use karma, but AGNs emit light in different wavelengths. So you can use radio emission to isolate blazars, X-ray emission to also detect sources that maybe doesn't vary in the optical range, but are still emitting in the X-rays. So yeah, there are several things. So we are also now trying to include more data sets. For the moment, we just use WISE and ZTF, but we hope to include also X-rays data and radio data in order to be able to detect them easily.
There's
from the side of...
Sorry.
from the sign of variability, that's we are using most of the features that we can use. And the difference between the numbers is just the band. So 1 means G band and 2 means air band. Okay, and another set of features that are very used by the community to characterize likers of AGNs is the damp random walk modeling. So this is the function. This is just an stochastic function where you have, it's like a random walk model, but you have a damping term that moves the liker all the time to the mean, so it doesn't explode. So you don't have likers that goes all the time up, 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 and then to infinite, because that's not realistic. If physically it's not possible to have a liker that all the time goes brighter. So you need this damping term here. And you have also, sorry, this is the damping term, the time scale. And this is the amplitude. Okay, so this is very used in the AGN community. And here I'm plotting these 2 parameters, the sigma, which is the amplitude of the variability at short time scales, and tau, which is the time scale of the variability for AGNs, quasars, and blazars. So these time scales tells you for how much time the liker is correlated. Okay, so let me see. Let me show you an example of a liker. Okay. So this is a nice example. So here, for instance, you can see that in this part of the liker, there is still some memory. So this point follows more or less what is happening here. But what happened here has nothing to do with what happened here. So how much time you can retain memory is the time scale of the variability. So that's what we measure from the damp random walk model. Okay, and when you plot that for AGNs, quasars, and blazars, you have this. So in general, quasars have longer time scales. They vary in the variations are slower, and the amplitudes are also smaller. So you have longer time scales and shorter amplitudes. AGNs tend to have shorter time scales and longer amplitudes, and blazars have much longer amplitudes and shorter time scales. So from this, you can see that we can also separate these 3 classes. So this is produced because we expect that sources with higher black hole masses will have longer time scales in the variability, and the quasars are the ones with the higher masses. So you see them in the area where you have a longer time scale in the variability, and AGNs have lower luminosities, so they have longer amplitudes, because we know that there is an anti-correlation between the amplitude of the variability and the luminosity in the optical range. And this is also detected in the X-rays, but for regular quasars or AGNs. So if you go to extremes like liners, there everything is different. But if we consider AGNs or quasars, they follow this relationship. So you have longer variability amplitudes for less luminous sources, and longer time scales for more massive sources. So that's why you have this plot. And for blazars, the behavior is different, because you're not observing emission from the accretion disk, but you're observing the jet. So everything is different, and the variability is much rapid. Okay, so and this was also seen by previous analysis, like this paper. So that's the end of the notebook. I think I'm just in time. Let me know if you have further questions.
Yeah, so if you have more questions, you're not sure to ask, you can also ask during the next session in the hands-on tutorial.
Yes.
And also, if you are going to join the next session, please stay in this Zoom link.
Ah,
There will be
is
two
this-
parallel. There will be two parallel sessions.
ah, okay.
So no questions.
Okay, I will stop sharing.
So we'll see you then in 15 minutes. And thank you, everyone. Thank you, Paula. That was a great.
Okay, thanks.
Patricia raised her hand.
Oh,
Yeah,
Ah.
sorry. So maybe we can talk during the break. But Paula, when you join the, like in the last bit, when you're joining columns to the catalog with the features, can you also join this catalog by rack sheet? So we have black hole masses for those galaxies where it's available.
yeah, but in that case, you don't have to do it like we are doing now, because we are using the object IDs. But in that case, you need to do a cross match between the. So you can use AstroPy to do a cross match. Yeah, but that's possible. And actually, let me show you, since you're asking. Let me. So we have done that for some sources, and we put the plots in the paper. So maybe that's interesting for here. So let me search for it. So in the appendix of the paper, we discuss in more detail the results of why. Okay. So this is the Leica classifier paper. And here you can see different properties obtained from SDSS spectra for redshift, sorry, for AGNs and quasars. We have redshift, black hole mass, luminosity, and electron ratio. And what we are finding is that where the two populations from the label set overlap, we are also finding a lot of confusion in the classifier. And it's produced by this difficulty in making strict cuts to separate these two classes. And because the labels come from Miliquas, who probably doesn't provide the correct labels for all the sources. But yes, you can do that, but instead of, sorry, let me share again. So instead of doing these joins, that in pandas, what you do is, let's see here. Okay, so when you do this join, you are joining by using the index. So this is the index of the tables. So what we need to do if we want to cross-match with another catalog is use AstroPy that provides a cross-match function. Or you can use TopCat. I hope that answers your question.
Okay, let's stop here. Thank you, Paula.
Okay.
We'll be back in 10 minutes.